So section 5.5 in the unit 5 for AP chemistry is called the collision model. And the collision model to me is actually where the content of kinetics should start, because all reactions have to start with reacting particles or the reacting molecules colliding. And there are three things that we need to have for a reaction to proceed. The particles must collide, and this is all part of collision theory. And then the particles must collide with sufficient energy. So I'm just going to put sufficient collision energy. And then the last one is that they have to collide with the correct orientation. And then below I have a reaction that we'll use as an example in two pictures of how this should proceed. So again, collision theory has kind of three main things, and that's the particles must collide, they have to collide with sufficient energy, and the correct orientation of the collision must happen also. So here is the reaction that we're going to look at. It's just what's called the ethene molecule reacting with hydrogen chloride gas instead of hydrochloric acid, and then it's going to produce the other particle that we're creating here, which is kind of like an organic particle as a product. So I have two collisions here. Collision one is where the hydrogen is aiming towards the double bond in that ethene molecule, and collision two is where the double bond is not where the hydrogen is going at, it's actually going towards the other hydrogen. And so for this, kind of a drawing or example, kind of think about which collision is going to be what's called effective, meaning they have to collide. They have to collide with the right amount of energy, which I'll talk about next, which is called activation energy. But then the collision has to have the correct orientation. And they found that the correct orientation, so I'm just going to say like yes for this one. This one is a collision that will be effective. And then this one is sort of no. So even if they collided with the sufficient amount of energy, they are not going to have the bond break in order for there to be products formed. So the last thing is if there is enough activation energy for the bond to break. So activation energy is really important in chemistry, and it's defined as the minimum amount of energy. So the minimum required energy to have the reactant particles react. So to have the reactant particles react. And maybe you've heard it before. We've actually talked about it probably in past chemistry units. But it is very important in chemistry that we know what activation energy is, and it's given the symbol capital E lowercase a. And again, it has to do with that sufficient energy that particles need to react. But they also, again, will still need to have the correct orientation. And this can kind of be summarized in something called the Maxwell Boltzman distribution. Again, maybe this is something that you have looked at before with gas laws. And the first question that I have kind of for you is to think about is which temperature, so T is temperature, which temperature, temperature 1, so that's the first temperature that was graphed here. And then T2 obviously is temperature 2. But the question is which temperature is the higher temperature? And sometimes that's even asked on the AP exam, is to say which one is the higher temperature and then justify your answer. And the answer is that T1 is a greater temperature than T2. And the reason why is you have a greater distribution of particles at a higher energy. So the area under this curve is like the same amount of particles as this one. But what they did was they basically ran this experiment at a higher temperature, so more particles had an average that was a higher kinetic energy. And then at this one, they have, the average is here, so more particles have a lower kinetic energy for the temperature that's there. So that's the first thing that you want to recognize with the Maxwell Boltzman distribution. And then the other thing that you're going to notice on a Maxwell Boltzman distribution is where is the activation energy. So what I'm going to do is just say that the activation energy is like right here. So this is the energy that's sufficient to create a collision that could break a bond as long as it's the correct orientation. And so what happens is if I kind of draw a line straight up here like that, okay, that's kind of the sufficient amount of energy for bonds to break and then for them to make products. So this is the number of particles. That little tiny amount kind of made it really drastic. That's the amount of particles that have sufficient energy at temperature 2, the lower temperature, to react. And then all of these particles under the curve, the number of particles, have sufficient energy to react. So at higher temperatures, I'll give you a little summary of this. At higher temperatures, there's more particles with sufficient energy to react. So I'm just going to sort of write that on the side here, that what this area represents here at the either temperature, you know, the low temperature, which was this small amount, or the higher temperature, which is this much larger amount, is that's the particles, or the number of particles with energy greater than the activation energy. And I'm just going to put EA for activation energy just to save some room. So the particles with energy greater than EA and have enough energy to react and then as long as they have the correct orientation, bonds will break. So I'll put a little disclaimer here that as long as, you know, as long as these particles have correct orientation. Sorry, that's a little bit messy. But again, I'll kind of read that off. The particles with energy greater than the activation energy and have enough energy to react. Again, as long as they have the correct orientation. So this does go back to the kinetic factors of how reactions proceed and what they kind of need or what can make a rate faster. So I'm going to do at the very top here is sort of list of factors that make a reaction have a faster reaction rate. Doesn't necessarily create more of that product. It just happens in a shorter time. So I'm just going to put up here kind of some factors that increase the rate of a reaction. And we just have one of them right there. Just going to rewrite this again. My stylus today is giving me some troubles. Rate of a reaction. So I'll just list. There are more than 3. One of them is surface area, but I'm not going to bring that up right now. One of them is what we just saw. So if we increase, just put an arrow, we increase the temperature, we will have more particles with sufficient energy to react, as long as they have the correct orientation. The other thing that can help is if you just have more particles. So they'll say like more moles of particles or a higher concentration of particles. And then last but not least, you could also decrease the volume, which is another way to increase, the concentration. But the big one here with the collision model is obviously the temperature, creating a higher quantity of particles that have sufficient energy to react. All right, well, I hope that was helpful. And this section, in my opinion, should really be covered first. So this is a little bit later. At least you know that these are the factors that particles need to collide and react.